Decision tree is a supervised machine learning algorithm where classification is done using decision tree structure. Here classifier tries to establish best suitable rule on which classification can be done, and the entire process is something like if this then that. Decision tree structure contains root node, branches, decision node, terminal node or leaf. Root node is the place from where structure starts and it splits into branches based on some rule. If each branch can further split on some condition, then this is called decision node, and if it cannot split further, it is called terminal node or leaf. Let us define few more terminologies to understand this algorithm. First is entropy. Entropy is nothing but measure of randomness or unpredictability of dataset. Lesser the value, better the predictability. Entropy is defined on dataset level, therefore it is denoted as HS, which means entropy of S. Less entropy means less randomness and better predictability. Entropy is equal to 0 means all instances belong to same class, which is the case of best possible predictability. When entropy is equal to 1, this means instances have all classes with exactly same number of occurrences. This is the worst case as far as predictability is concerned. Entropy between 0 and 1 means classes are unequally distributed within instances. When we plot a graph between entropy and probability, we get something like this. Entropy is 0 when probability is either 0 or 1. This is only possible when all instances belong to same class. This is the situation where predictability is best achieved with highest accuracy. Entropy is 1 when probability is 0.5, which means all classes have exactly same number of occurrences. Prediction becomes most inaccurate under this situation, but these two situations represent two extremes or two boundaries. In realistic datasets, we hardly get this. Rather, entropy lies somewhere between 0 to 1, like it may be 0.91 or 0.94. Information gain is defined as relative change in entropy with respect to an attribute A, and it is denoted as Ig as comma A. And it is calculated as entropy of parent minus average entropy of children. Information gain is defined for a particular attribute within a dataset. Therefore, it is denoted as Ig s, A, which simply means after adding or removing this attribute, by what quantity entropy will change. Information gain is a key factor in building decision tree. In this way, entropy is always defined for entire dataset, but information gain is defined for each attributes. For example, information gain for outlook will be denoted as Ig s, outlook, and for temperature it will be denoted as Ig s, temperature, and so on. Decision trees can be built using many algorithms, but most common one is ID3 algorithm that we will discuss here. We create the root node, and if all examples are positive, it returns leaf nodes positive, and if all examples are negative, it returns leaf nodes negative. Otherwise, it calculates information gain for each attribute, and the attribute having maximum information gain becomes the decision node, and this attribute is removed from dataset. Entire steps are repeated recursively till all attributes are removed or we get all leaf nodes. In the above example, we have 4 attributes: outlook, temperature, humidity, and wind. Data is collected for 14 days to record when golf was played or when not. Now we want to build a classification algorithm that can predict when golf can be played and when it cannot be played based on outlook, temperature, humidity, and wind features. Here we go and we calculate information gain for each attribute, and outlook is the attribute having maximum information gain. We create a node for outlook, and since it has 3 discrete values, sunny, overcast, and rain, We create 3 branches for each. Since for Outlook attribute overcast instances are always yes, we return yes to leaf node. Outlook attribute is removed from dataset, and with remaining attributes we create 2 subsets for a particular value of sunny and rain. We call these subsets as sunny and as rain. Now again we find maximum value of information gain in each of the subsets, which is humidity and wind respectively. We add humidity and wind as decision node, and finally we end up getting leaf nodes having either yes or no values. This is the very generic overview of decision tree, but in reality trees grow very large and we need to regularize it so that it doesn't become too much data specific. In coming videos we will discuss other advanced aspects of decision tree algorithm in machine learning. Thanks for watching. Goodbye.